In this video I'm going to review the basic principles of binary numbers, and I'm going to do that by comparing a binary number to a decimal number. So I'll begin with the decimal number since that's the system that we're most familiar with, and I'm going to choose a 4-digit decimal number. So I'm going to fill in 4 digits here. I'll just choose a random number. There's no particular significance to the number that I'm going to choose here. Let's have 7,386. So for reasons which will become clearer as we go along, I'm going to number the digits in this number, beginning with the rightmost or the lowest valued digit, what we sometimes call the least significant digit. And I'm going to number that digit 0, and number the next one digit 1, next one digit 2, and next one digit 3. So these are the numbers of my digits. So the number is basically just 7,386, but let's break down exactly what each digit represents here. So digit 0, which is 6 in this case, is a multiple of 10 to the power of 0. And that is the same as 6 times 1. So any number to the power of 0 is equal to 1. So 6 times 10 to the power of 0 is equal to 6 times 1. And that, of course, is just equal to 6. The next digit is digit 1. In this case it's an 8. So this represents 8 times 10 to the power of 1. And that's 8 times 10, which is 80. The next digit, digit 2, in this case is a 3. And it represents 3 times 10 to the power of 2, or 10 squared. So that's 3 times 10 times 10. Which of course is 300. And then our final digit in this number, since it's a 4-digit number, is digit 3. It happens to be a 7, and it represents 7 times 10 to the power of 3, which is 7 times 10 times 10 times 10, or 7,000. So each of our digits represents a multiple of a different power of 10. Digit 0 is the multiple of 10 to the power of 0, digit 1 is the multiple of 10 to the power of 1, and so on. Now if I add up the contribution from each of my 4 digits here, 7,000 plus 300 plus 80 plus 6, all of them added together gives us the same number that we started out with. So 7,386, which of course is a decimal number. Now we often refer to the decimal number system as base 10, and that means a couple of different things, but primarily what it means is that the values that we have available to us for each of the digits in the number come from a list of 10 possibilities. So the 10 possible values of each digit in a decimal number are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 10 possibilities for each digit. One consequence of that is that the numbers end up being multiples of different powers of 10. Another thing that we can say about it is that if we were to look at the minimum value for our 4-digit number, what the minimum value that we could have got would be obtained by choosing the smallest value for each digit. Now I'm not going to consider negative numbers here, we're just going to assume that these are unsigned integers that we're representing, meaning that they're all going to have values of 0 or greater. So if I choose the smallest number that I can for each digit in my 4-digit number, I would just fill in 0 here, everywhere. And that of course is equal to 0. Conversely, the maximum value that we could have got for our 4-digit decimal number would be obtained by choosing the biggest digit value that we could for all 4 digits, which is 9. Now that number, 9,999, is equal to 10,000 minus 1, which can also be written as 10 to the power of 4 minus 1. So the biggest 4-digit decimal number we can have is equal to 10 to the power of 4 minus 1. So that's our decimal number example. I'm going to do the same thing now for a 4-digit binary number, and we'll see how the two number systems actually work in a very similar way, but there is one important difference. So I will choose at random a 4-digit binary number. And the first thing that we need to observe about binary numbers is that the binary counting system, or the binary number system, is base 2. And what that means is that the possible values for each digit come from a very short list, which contains only 2 possibilities, 0 and 1. So whereas for a decimal number there was 10 possible values for each digit, in binary numbers there's only 2 possible values for each digit, 0 and 1, and that's what makes it a base 2 number system. So I'm just going to fill in some random digits here. Let's just choose 1, 0, 0, 1. And as before, I'm going to number my digits 0, 1, 2, and 3. So beginning with the rightmost, or the least significant digit. So these labels here will just help us to keep track of what each of these digits represents. In binary numbers, incidentally, you will often hear the individual digits referred to as bits. So if I use that term here, I just mean the same thing as a digit in a binary number. So bit 0 here, or digit 0, which is 1, is the multiple of 2 to the power of 0. So that's 1 times 1. So again, any number to the power of 0 is equal to 1. So 1 times 2 to the power of 0 is just 1 times 1. That's equal to 1. Bit 1, in this case, happens to be 0. That is the multiple of 2 to the power of 1. So that's 0 times 2, and that's 0. The next digit, digit 2, or bit 2, again it's a 0. That's the multiple of 2 to the power of 2, which is 0 times 2 times 2, which is 0 times 4, that's 0. And finally, digit 3, or bit 3, in this case is a 1. That is 1 times 2 to the power of 3. So digit 3, or bit 3, is a multiple of 2 to the power of 3. That's 1 times 2 times 2 times 2, 2 to the power of 3, which is equal to 8. Now, as before, if I add up the contribution from each of my 4 digits here, I'll get the total value of the number. So 8 plus 0 plus 0 plus 1 is equal to 9 decimal. So the number that I originally wrote here as a 4-digit binary number, 1001, is just a different way of writing the number 9. So 9 written as a decimal number is precisely the same number as 1001 written as a binary number. They're just 2 different ways of representing the same number. As before, I would like to note the minimum and maximum values that we could have had for our 4-digit binary number. So the minimum would be obtained by choosing the smallest digit value available for all 4 digits. So that, as before, that's 0. And that, of course, is just equal to 0. However, the maximum number that we could have had for our 4-digit binary number is obtained by filling in the biggest digit value that we can for each of the 4 digits. Now, the biggest value that we have available to us for each digit in a binary number is 1. So if I fill in 1, 1, 1, 1 here, what that is equal to is 1 times 1 plus 1 times 2 plus 1 times 4 plus 1 times 8. So these are all the powers of 2, and that all adds up to be 15. Now, as I noted up here for the decimal number, there's a similar property here. 15 is equal to 16 minus 1, which is 2 to the power of 4 minus 1. So in a binary number, whatever number of digits you have can represent a range of numbers from 0 up to 2 to the power of the number of digits you have minus 1. So in this case, 2 to the power of 4 minus 1 is the biggest number we can represent with our 4-digit binary number. And that's it.